Okay, this is a presentation of the chapters on central tendency and variability. So central tendency describes where scores tend to be. So it's the statistical measure to determine a score that describes the center of a distribution of scores. So where scores tend to be, or where scores tend to center. So it's not as easy as you think, because the first thing you think is mean. Done. Let's move on. Well, not quite. The most obvious one is the mean, otherwise known as the average. As a population parameter, is referred to as mu, the Greek letter mu, or mu, like a little cat. As a sample statistic, is referred to as m, italicized, or x bar. M italicized is used more often now. X bar is kind of fallen out of favor. The sum of scores divided by the number of scores is the calculation for mean. It's pretty simple. So summation of x divided by big N would give you the mu for a population. And for a sample, it would be m italicized, the summation of x divided by n lowercase to indicate a sample. So that would be the mean for a sample. Mean is the balance point for a distribution. The total distance below the mean is the same as the total distance above the mean. Sometimes you do have to calculate a weighted mean, and that's when you have two groups and maybe one group is larger than another. So that would basically be summation of x, or the overall sum for the combined group, over n, the total number in the combined group. So summation of x sub 1 plus summation of x sub 2 over n sub 1 plus n sub 2. That's you won't encounter that much in this class, but you should be aware that this possibility exists. So if you're later trying to calculate a mean or do research in the field, you'll be like, oh, wait a second, I need to differentiate for weighted mean. So calculating a weighted mean, just a quick work example. You have the first sample has n equals 12. The second sample, n equals 8, gives you combined n of 12 plus 8, so 20. The summation of x is 72. The summation of x for the second sample is 56, so the combined summation of x is 128, or 72 plus 56. And the mean for the first sample, just looking at the first sample, would be m equals 6. And the second sample, we mean equals 7. And so the combined would be 6.4. And you would calculate that by taking below here summation of x sub 1, which is 72, plus summation of x sub 2, which is 56, over 12 plus 8, which is n sub 1, n sub 2, which equals 128 over 20, which gives you the value of 6.4. Now, I say sub. Some students have asked me that in the past. When I say n sub 1 and n sub 2, I mean n subscript 1, n subscript 2. So sub is just shorthand. So I'll say x sub 1, x sub 2, n sub 1, n sub 2. So that's what I'm saying. I'm saying sub or subscript. Okay. Sometimes we only have frequencies in which to calculate our mean. And to do that, we can just sum the f sub x value here, this column, which would give us the value of 66 divided by 8, which 8 is, we calculate the f's together. The f equals frequency, so 1 plus 2 plus 4 plus 1 will give you the value of 8, or the n. So that's another way to calculate mean if you only are supplied with the frequencies and the frequencies of x. So they're saying that there's one value of 10, so it's 10 here, and there's two values of 9, which gives you 18, and there's four values of 8, which gives you 32, and so forth. So that's just a worked example, that's not too common, but just for future reference. Characteristics of the mean. Changing a score will change the mean. It's very sensitive to fluctuations. So introducing a new score, removing a score will change the mean. Interestingly, adding or subtracting a constant from each score will change the mean by the same constant. So if you add 1 to each score, the mean is going to go up by 1. If you subtract 1 from each score, the mean is going to go down by 1. Uh, Multiplying or dividing each score will also change the mean. The median divides the distribution in half by marking the 50th percentile. Median is a little different. It's another measure of central tendency, and it's basically the 50th percentile mark. It's the middle score in ordered numbers. You're probably familiar with this from elementary school. So in a set of scores, what is the median? So you have 3, 3, 4, 5, 7, 8. Well, it'd be somewhere between 4 and 5, so 4.5, because 4 plus 5 equals 9. 9 divided by 2 is 4 plus 5. 4.5, sorry. So it's the score that has the greatest So that's the median. And so mode is the score that has the greatest frequency. It's most appropriate with categorical or nominal variables. So variables like gender or student classification. So in this set of scores, the mode would be, what's the most frequent score? So you have 2 3s, so it's going to be 3. So which measure to use? That's to use mean, median, mode. So when scores are skewed, the mean is typically considered easily influenced, so thus median is better. When there are undetermined values, open-ended values, ordinal scale values, the median is also better. So when you have this uncensored or undetermined values, the median is also better. But how do you tell skew? You tell skew is wherever the tail is. If the tail is on the left side or toward the lower numbers, then your distribution is negatively skewed. If the tail is on the right side or toward the higher numbers, then your distribution is positively skewed. So let's look at skew versus skew. So positive skew is where's the tail? The tail is toward the higher end of the numbers going left to right. So if one would start here through 10. So if the tail, the distribution is over here and the higher numbers is positively skewed. Now if the tail is on the lower end of the numbers right here, then it's negatively skewed. So which measure to use? So for nominal discrete variables, mode is better. To describe the shape of a distribution in terms of peakedness or kurtosis, mode is also better as well. More on shape, visually you can see that depending on the skew of the distribution, mean or mode might not be the best representation of the measure of central tendency. So you can see when in these skew distributions where A is, that's right, it's positively skewed, and B is negatively skewed, median is a better representation of the measure of central tendency, because the mean is pulled by the outliers or the skewed nature of the distribution, while mode isn't, went too fast, and where mode isn't getting pulled at all. Okay, so now variability, which is a quantitative measure of the degree to which scores in a distribution are to spread out or be clustered together. So are scores really clustered together or are they spread out? So we have A, which is the distribution of adult heights in inches. And then we also have B, which is the distribution of adult weights in pounds. So you can see that the distribution of weight is much flatter and less kurtotic or less peaked than the distribution of height. The difference between the upper real limit and the lower real limit of the largest score value and the lower real limit of the small score value is our range. The range is the most common measure of variability that you'll encounter because it's the most basic. So that's probably the one you learn in school. So range, so upper real limit minus lower real limit. Or you could say highest score minus lowest score plus 1. Another measure of variability is the interquartile range, which is Q3 or Q sub 3 minus Q sub 1. And it basically covers the middle 50% of the distribution. So it describes the variability for the middle 50% of the distribution. But wait a second, where did these Q's come from? What is that? Q basically stands for quartile, but more specifically, Q sub 1 is the 25th percentile, Q sub 2 is the 50th percentile, the median, otherwise aka the median, and Q sub 3 is the 75th percentile, and Q sub 4 is the 100th percentile. So interquartile range is the 75th percentile minus the 25th percentile, leaving you the middle 50. So how do you find Q1 and Q3? So let's take a set of scores, 3, 7, 12, 8, 5, and 10. First, we need to order our data. So order it from least to greatest, 3, 5, 7, 8, 10, and 12. Then we divide them into upper and lower halves. And then you find the median of the lower half, which is 5, and this is your Q1. And then you find the median of the upper half, which is 10. And this is your Q3. We also have semi-interquartile range, which is half the interquartile range. So find your IQR, your interquartile range, and divide by 2, and you get your semi-interquartile range. Population standard deviation and variance. Standard deviation and variance are very common. You'll be using them predominantly in inferential statistics, and which you might not have exposure to depending on how much math you had in your past. You need to get comfortable with it. It's not going away. It's definitely not going away. So let's start with the steps to calculating variance and standard deviation. Oh, too fast. Okay, to find population standard deviation and variance, first you need to find all the deviations of each score from the mean. So basically x minus mu for the population. Notice the use of mu. So if let's say we have where mu equals 3, and we have the scores for x of 8, 1, 3, and 0. So x minus mu would be positive 5, then negative 2, 0, and negative 3. And then you add those up, and if you added those up, you would get the score of 0. And this would happen each time because, why? Mean is the balance point of a distribution. So what do you have to do to solve that problem? You have to square each deviation from the mean. And this is where you may have read already about sums of squares. So sum of square deviations from the mean. So if we don't do that, we're going to end up with a value of 0. So SS, or sum of squares, can be calculated as, the definitional formula is summation of x minus mu squared, or x minus mu squared summation, or a computational formula is sum squared equals a sum of x squared minus summation of x, parentheses, squared over x. To continue our calculation of standard deviation and variance, the sum of the squares of each deviation from the mean, or each x minus mu, also known as sums of squares. So we sum those values up, each deviation. Then we take the sums of square value and divide by n. This is the population variance. So sums of square divided by n is your variance, or sigma squared. Variance is really just the mean of the squared sum deviations. So that's another way of thinking of it. So standard deviation, or sigma without the square, is the square root of the variance. So standard deviation is the square root of sums of squares over n for a population. This formula is mostly the same for the sample standard deviation with a slight change up. First, we find all deviations from the score from the mean, just as before, where in this case the mean would equal 3 instead of the mu. And now this mu should actually be an m. And remember, if we don't do this, if we just add up those deviations, we get a 0 because the mean is the balance point of the distribution. So what's wrong with this slide? Remember that this mu value should now be an m for mean, for a sample mean. And then we sum it as we did before. So in this case it's 40. And then we take the sum square and divide by n minus 1. N meaning lowercase is the sample number of scores in the sample minus 1. So sum squared divided by n minus 1 will give you the variance, and the square root of this variance will give you the standard deviation, otherwise known as sums of square, otherwise calculated sums of square divided by n minus 1 square root. So what's n minus 1 about? Why are we doing minus 1 all of a sudden? We must divide by n minus 1 to calculate correct standard deviation and variance. Otherwise, our standard deviation and variance tend to be underestimated. So n minus 1 refers to our degrees of freedom. The degrees of freedom refers to the number of scores that are free to vary. And what do we mean by that? So it's like saying you have 4 cards in your hand. Now, if one of those cards you know is going to be held constant, like the population parameter, this is actually exactly what it refers to, you're assuming you know the population parameter, that your mean approximates that, but you don't actually know. And so you have to subtract 1 score from your values to obtain a more accurate estimation. So, going back to the card example, sorry. There's a population of 52 cards. This is a sample 4 cards. The mean value of these cards is 10, as they're all, in the hand was 10, 10, 10. Wait, 10, 10, 10, 10, 4 tens. So summation of x is 40. N equals 40. Remember the first step in calculation, calculating standard deviation for both a sample and a population. Find that all the deviations from each score from the mean. Going back to the mean. So we're assuming we know that the mean is that the mean we have for our sample of these 4 cards is an accurate representation of the total card population. We're assuming that. But we don't actually know that's true. So we need to subtract 1 value, n minus 1, saying that one of these values is probably off. So we're assuming that our sample mean actually represents the population. Thus there goes 1 degree of freedom, n minus 1 with that assumption. So in a population of scores, the mean would represent the population. Thus n remains the same. So in a population, in calculating population, you know your mean is right because it's the population. But for a sample, you hope it's right, but it's really an approximation. So you have to do n minus 1. Unbiased versus biased. An unbiased statistic is equal to the population parameter. We want our statistics to be unbiased. A biased statistic consistently over or underestimates population parameters. Characteristics of standard deviation. Adding a constant to each score will not change the standard deviation. Multiplying each scores by a constant causes the standard deviation to be multiplied by the same constant. Oh, wait. Yeah, multiplied by the same constant. So those two characteristics are important in distinction from mean. So that's the presentation for the central tendency and variability chapters. Please contact me with any questions.